everyone. Can you hear me? I would like to confirm the speaker of the 4 paper for the best paper selection section.
I can hear you.
Okay, good. So you are readers? Oh no, you are an attender?
Yes.
Okay, great. You will be the third paper. Okay. Okay, good. And how about the other speakers? Because now the keynote speech is still ongoing, so yeah, maybe we still need to wait for maybe 10 minutes to start this section.
Understood. I just want to confirm the length of the talk.
Yeah.
Recently, email says 12 to 15 minutes. Is that correct?
Yes, totally 15 minutes. Yeah,
Okay.
because we need to take 5 minutes for Q&A. Yeah.
Okay. Sounds good.
Okay. Vinod, can you hear me?
Yes.
Okay, you are the second paper, right?
Yeah.
Okay. Oh, you. Okay, good. I would like to confirm the other speaker. Still cannot see other. Oh, Pradeep, you will do the presentation? Okay. I don't know how to grant you with the panelist permission. Could you try to log in with the other password? The password should be bigmm@2020. So if you log in by that password, you could become a panelist.
Hello, this is Ralph from Germany.
Okay, thank you for trying. I'm still confirming the first paper, the presenter for the first paper.
Hello, Ralph and Jianquan, everybody. Is Roger from
Great.
Singapore?
Roger, thank you.
Hello, Roger. I also had a problem first with the password. The first time I tried the password didn't work. The second time it did work.
Okay.
I typed the password, then I did use the regular password, and then I used the panelist password again. Now it's working. Hello, Roger.
Hello, hi, Ralph. Hope you're doing well.
Yeah, a bit early, but everything is okay. I had to try this a bit before. No, everything perfect.
Oh, yeah, right. It's 6:30 a.m. for you, right?
Yeah, but I had to try a bit before, so I get up just right at 5 o'clock to see what's happening, to look at the papers, and to see all the emails here. Okay.
Yeah.
Oh, thanks.
Okay, for me, it's a good time. Yeah, it's just around lunchtime, so it's good.
We still cannot find the first paper, the presenter. Okay. Oh, who is the host? The Midas. The Midas is the host. So could you try to promote Pradeep as the panelist? And also I see one attendee is raising the hand. I'm not sure. I cannot unmute his mic. Please unmute his mic and let the attendee can speak.
Excuse me, sir. So, do you want us to make Mr. Pradeep the presenter?
Yes. He will be
So
the
I think
presenter
he
for
hasn't
the
joined
whole
with
paper.
the right panelist link. So he has to join using the panelist link so that we can make him the presenter. Just a second, we'll check it.
How can I'm not sure. Can you do the promotion now? Because you're the host.
So I'm not the host. I'll be telling the host to do so. Just 1 minute.
Okay, how can I do it? Let me send the URL again, and it's the problem to happen.
So we're making Mr. Pradeep the host. Just 2 minutes.
Yeah, please try it.
So Mr. Pradeep is now the panelist also. Should we make him the presenter also?
Oh, great. Okay. I'm still confirming with the first paper. I cannot see the presenter of the first paper. Oh, Pradeep, good to see you. You present the paper instead of your student? Your mic is unmute. Your mic is muted now. Okay, please unmute your mic to speak.
Hi, hello.
Hello. You will do the presentation instead of your student?
I think I have the fourth presentation today.
Okay.
Right, so the last paper in this session.
Okay. Yes. Great. Thank you for confirming.
No problem.
Where's the first author? actually it's the time for this section, but I cannot see the first author or the author for the first paper. Let me try to confirm the list of attendees again. Yes, Aaron, thank you. I noticed the first paper, but I cannot find the author of the first paper from the attendee list. Okay, anyway, we should change the order for the presentation. So I have to start the section for this first paper selection. Actually, because now we have the delay for 2 minutes. So at the beginning, I would like to invite the second paper. The speaker would be, please prepare your share to share your desktop. Pradeep, please unmute your mic.
Sure.
Okay, thank you. And before starting this session, I would like to introduce the basic information for the presenter. At this section, actually, we have formed a award evaluation committee within 7 members. They are all well-known professors or researchers from both academia and industry, including like IEEE or ACM fellow, seniors, and the professionals. And the presentation time will be strictly controlled. And the first bell will be at 12 minutes when you should complete the presentation. Like this is the bell. Can you hear the bell? The sound of the bell? Okay, good.
Yes.
And the second bell will be at 50 minutes. Like this. You should stop your presentation. And the third bell, like this, at 20 minutes finally, okay? Yeah. You can, if you are ready, you can start your presentation. Pradeep, please also close your video at this moment. Okay, thank you. Great. So for the second paper, Vinod.
Yes, but I'm seeing the sharing option is disabled for me.
You cannot share your desktop?
Just a second, sir. We'll be making Mr. Vinod the presenter.
Yeah, we will just let us know, Dr. Liu, whom to make presenter, we will make.
Okay, I need to set the presenter, right? Okay, let me see.
No, sir, we'll be doing that. Just a second.
I cannot do it.
So you can just let the volunteer know, he can do.
Okay. This. Oh, yes, yes. Are you ready?
Yes, I'm ready.
Okay, okay. Please start your presentation.
Thank you, Dr. Liu. Hello, good morning all. I'm Vinod Chhapariya. I'm going to present my work on tag-boosted hybrid recommendations for multimedia data. This is part of my MTech thesis under the supervision of Dr. Manish Singh and PhD student Sailaja Rajanala. So in this work, the recommendation systems, we predict the user responses, user preferences to the given options or the web items we have. So when it comes to the multimedia data, we have less textual information available, like most of the data is in images, audios, and videos. So such example is, we can see the movie lens data, which has, let's see the movie lens example, where for the movie Star Wars, we can see these standard features like genre, directors, cast, etc. And also we see the movie plot, which talks about what the movie is about. Interestingly, here we can see the tags also in the bottom. Like there are a lot of tags with their frequency, the number of times this particular movie tagged with those tags. So with this basic introduction, let's look at the recommendation approaches we have. So content-based approach, where we extract the features from the items and we build the user's content profile and we start recommending. But like for multimedia data, it's difficult as we don't have that much textual information available. So, and also in content-based approach, like system recommends only with respect to the user profile. Whereas in second approach, we have the collaboration between user and item where the user history is available. But that approach is also suffers from the cold start problem where we don't have initial ratings, and also the utility matrix which we get from user item collaboration is sparse in nature. So can we get the best of these? Yes. So we have the hybrid approaches where we integrate the two prior systems and come up with a better recommendations. So as we all know, while getting the recommendation, we like feedbacks are very much important. Without the feedbacks, we can't understand like what recommendation we should proceed with. So broad categories of the explicit feedback, where the ratings, review, like comments we take from the users and ask them to give that feedback. So, but with respect to ratings, the problem is we can't interpret why that rating is coming for the particular web object or the item. Whereas in implicit, user don't even realizes he's giving the feedback, like in terms of like, share, or tags, etc. And can we leverage this implicit feedback, especially in multimedia data? Let's say the example of the tag. So in this work, we concentrate on the tags. We try to harness the tag information and make use of that information to improve the recommendation performance. We can see here the users tag the particular item with some tag, and that gives us the ternary relationship between user, item, and tag. So tags as a feature of the item, and tags also the collaboration between the user and item, that gives us the content-based and collaborative aspect that the tag information provides us. So with this background, we formally introduce our problem, like with respect to the tag, whether the user tags the item, we build the user item tag metric based on that. And formally, we define the problem here. So there are m users and n items, and we are finding the association, like the user m is tagged by the item, uh, item n is tagged by the user m with some tag t. And then we say that this user might be interested in that particular item. And we make the rating as 1. And if tagging not done, then we say that maybe the user is not interested or not aware of that particular item. So recommendation task here to predict whether some item nj will be potentially tagged by user m with some tag. So while solving this problem, the approach we follow is, we in first approach, we consider the tags as a features of the item, whereas we consider the tags as a vocabulary of the item, and we come up with the latent representation of the tags, which gives us the content representation of the item, and then we recommend based on that. In second approach, we explore the user item tagging matrix, which we got from the user item tag ternary relationship, and we use the standard collaborative filtering method, matrix factorization, and we come up with the latent factors. And finally, in third approach, which is our proposed technique, we combine the best of these two, like the latent representation from the tags from the topics and the from latent factors, and we integrate in such a way that we get the boosted performance for the recommendation. So let's start with the first approach, where we adapt the topic modeling on the tag information. As we all know, topic modeling is a dimensionality reduction technique, where we every document is splitted into topics, and we find the topic proportions, and then for each topic there is a word probabilities we try to calculate. With a similar analogy, we apply that on tags, and we build the tag latent topics out of it. So the famous topic modeling algorithm is LDA. So we adapt this LDA on the tag information and try to find whether this particular tag will potentially be tagged to the particular item. And with this, we come up with the topic proportions vector for each item. And with that vector as a latent representation of the item, we try to recommend using the simple cosine similarity and taking the inner product of the user latent vector and the topic proportion vector which we get from the LDA. So second approach, where we use the collaborative aspect, like user item tagging matrix. We use the standard matrix factorization on the tag, and using that we get the user and the item latent vectors. But we are interested here in probabilistic matrix factorization because we want to integrate the both. So where we like the atom and the user latent vectors come from some distribution, here in our case normal distribution, and we tune the rating with precision parameters, and finally we learn the parameters and get the user and atom latent vectors from the probabilistic matrix factorization, and then we able to recommend the prediction. So now coming to the proposed model. Here is the graphical representation of the model we developed, the tag boosted hybrid method, where you can see from the topic proportions theta giving the content representation, latent content representation, and from the epsilon, which gives us the latent offset of the item, and we integrate that to boost the rating performance, recommendation performance. So here, the way we integrate is a probabilistically we call this epsilon j as a atom latent offset, and we integrate with the topic proportion, and that's how we are able to provide the both. Like this latent offset controls the collaborative aspect of the item, whereas topic proportions give the content aspect of the item, and we form the same objective function as matrix factorization, and we take the expectations for the topic proportion and the latent offset. So coming to the recommendations, so especially in terms of multimedia data, when we have let's say no user history available, still we are able to recommend based on the latent topics we have. And if we have both the content and the user history also, then we use the latent offset, and then we are able to give the more better recommendation performance. So evaluations. So to implement this technique, we have used standard movie lens 20M dataset, where we have the 465K tags, and we also took one more dataset like movie lens with plots, like movie plots, and then we applied the stratified sampling on the both movie lens tag and the plot, and then we could see that there is a better performance. So stratified sampling is done like selecting some good tags, and some filtering is performed. Also on the plots, we use the rake algorithm to extract the keywords. So from that, this is our experimental setup where we do the standard 5-fold cross validation, and these are the tuning parameters we used. These are experimental settings for latent topics, latent factors, and tag boosted hybrid method. So evaluation metrics is standard recall ATM and mean average precision we have taken. So yeah, so Now, when we see at the results, the first blue line, we see like the latent topics. Like from the plot, movie lens plots, we could see the recall is low. But when we see in the tags, we can see the latent topic performance is increased. That gives us the interpretation that the tags understand the content in a better way than the plots. And also, we could see the final performance boost on the tag for the tag boosted hybrid model, the TBH. We could see that 15 to 20% improvement in the results. And also, as I told, like before stratification, results were not that good. But when we went with the stratification, then we could see there is a huge performance boost. And then this shows that having a meaningful tags gives a better recommendation performance. Because that leads to getting the good topics which represent the content well. So also we compared our this tag boosted hybrid method with one of the hybrid recommendation baseline method where the same way that hello.
Hello, what happened?
Yeah, I guess presentation. Hello.
Yeah, we cannot see your presentation.
Yeah, so all of a sudden it went, I guess. Hello.
Could you please stop and present again? I mean, from the slide. Yeah.
Yeah. Let me share again.
Okay, I will stop the bell.
Can you see now?
Yes, we can see your desktop.
Yeah.
Okay. Yeah,
so all of a sudden screen disappeared. So I was talking with the
please.
Yeah. So hybrid rec where we compared like when we use the tag boosted hybrid, we got a 10 to 15% better performance than the baseline. And also the second metrics like mean average precision. So we could see here also like there is a we got a good performance on the tags when we compared on the plots. So that says if we effectively use the tags, then it can gives us the good content representation of the item, especially when it comes to the multimedia data sets. And also like user item collaboration with respect to the tags, that tagging utility matrix gives us the user history where we have the recommendations from the collaborative user history perspective, and that improves the recommendation performance. And also comparison we saw on the movie lens tags and the plots. It's like we could see there is a boost like tag understand content better way. So thank you.
Okay, good. Yeah, time is perfect. Okay, I think the evaluation committee members should have as many questions as possible. Yeah, please try to unmute your mic and ask some question.
I have a couple of questions. This is Vishy. The first question is, in order to use tags, almost instead of ratings or some other implicit feedback, you do complete the matrix. Do you assume that everybody who's watched the movie in this example actually also tag, or is that a subset?
Yes. So as I understand, like everybody may be not aware of all the movies, or the tagging is not happened for all the movies. But in that case, that's why like maybe user is not aware of. So by default, we are taking that rating as 0. Whether rating 0 here doesn't represent the user is not interested. Maybe he has not seen that movie, or he is not aware of that. So is that answers?
Partially. There were two parts to that question. The question really is that in order to complete the matrix, the assumption is that you're going to recommend the top 10 that would fit this user. user's interest, right? Now, if you don't assume that a user has actually watched a movie but not tagged, you may end up recommending the same movies to the user that the user has already watched.
Yeah, but in that case, we need users, like we are considering the both the way here. Like if the user history is not there, then the recommendations will come from the user content profile, or maybe based on the whatever the little history we have from the users. But if in case of no user history, we will be able to represent from the latent topics like content of that particular user's profile. So if he has not tagged also, but we know this user based on this is similar tags and like the previous tags we can.
Thank you.
Yeah.
Okay. Any other questions?
Mr. Vinod, good presentation. Okay.
Thank you, sir.
Mention that in this work you have compared your hybrid model with the individual models. Okay.
Yeah.
What about comparison with your state of art?
So, state of the arts, they explore with the deep learning models and neural networks. But here we use, without going for the deep learning, we just use the latent representation from the modeling. And our focus is to make the probabilistic probabilistic model which can leverage the tag information here. So,
No, I guess that other than deep learning, there are also some methods which are not involving deep learning models.
yeah.
So have you not looked into those works and thought of comparing with your proposed model?
Yes, sir. So we have thought of that, but here our novelty is to effectively. That may be the extension work of this particular approach we are especially for the multimedia data where the tags and we wanted to effectively use in such a way that we get, without getting explicit feedback, we get the good recommendation solutions.
Okay, thank you. Thank you.
Yeah.
Okay, good. We still have more than 1 minute. Is there any other question?
Yeah, hi Vinod. This is Roger. Thank you for a nice presentation.
Yeah.
I believe you mentioned in one of the slides that you filtered out some of the less common tags.
Yeah.
Yeah. I mean that is quite often done, but aren't those also the kind of the more difficult cases to predict if you have tags that are not very frequent? Is your method able to handle those cases? Recommendation systems always have this issue of, as you mentioned, cold start and items that are not very popular.
Yeah. So that's why we did this. We had the genre as a criteria when we selected top 1,000 tags. So like Movilin's data set, we gave the genres. So we took the help of genres where we cover, like we wanted to make sure we cover all the genres and top 1,000 tags from those genres. So that covers that inclusiveness of all the tags we have. Like we are not just giving a priority to the tags. We are, let's say, the science and picture or the animation. These are very broad tags. So that's why we go genre wise, and every genre there are 18 genres in this Moviling data set. So we selected. So that gives us the diversity of selecting the tag.
Okay, thank you.
Yeah.
Okay, great, perfect. Time is over, and yeah, your presentation can be finished within 20 minutes. It's perfect. So thank you again, Vinod. Thank you for your presentation. And let's go to the next paper. Actually, the first paper, the presenter of the first paper is here, but the paper will be not presented by the author, instead by the other team member. Okay. Zhang, who's the presenter is the Zhang Zhongyin.
Yeah.
You will present the paper. Yeah, please prepare. If you are ready, and you can start the presentation.
Okay. Can you see my screen?
Yes. Yeah. Yeah, please start your presentation.
Okay. Good morning, everyone. My name is Ying. Today, I'm really glad to introduce our team's paper titled Trajectory Similarity Assessment on Road Networks via Embedding Learning. Okay, with the development of mobile technology, a large number of trajectory data have been generated in people's lives, which can be collected by GPS, AIS, and other devices. Trajectory data contains rich information, and it is widely used in many fields such as urban planning, intelligent transportation, and location-based surveys. Where our research focuses on a basic task, trajectory similarity assessment. Where because of the limitation of real-world device, vehicle trajectories usually have some constraint. For example, the road networks are complex and intervened, and the sampling rates of vehicles on the same road are different. What's more, there may be some weak signal or damage with GPS equipment, which will lead to big differences between the actual GPS information. So in face of these difficulties and challenges, a lot of previous studies have proposed creative methods of trajectory similarity assessment. These methods can be classified into two types. The first type of approach is build efficient index structures for similar trajectory queries, where the second type of approach is design trajectory similarity measures to evaluate similarity, such as most classic measures ETW and RCSS. Recent measures add spatial context and information of projection in model. We extracted trajectory features by using the encoder to optimize similarity calculation, but he failed to consider features of the zone network. Although these approaches just mentioned have achieved relatively good results, but only a few models can fully extract trajectory features from the zone network. And most methods are time-consuming. For example, the time complexity of these approaches is always O(m squared). So why can't we get better results? It is obvious that the zone network can be seen as a spatial graph. But different from social networks, zone network is not only topology, but spatiality, which usually be ignored by researchers. So we propose a zone network embedding to capture these two characteristics and optimize the spatial correlation of the loss function for trajectory similarity assessment. Okay, before we start with the model, let's look at a few definitions. Suppose x is longitude, y is latitude. We use a continuous XY sequence and mark it as t to represent the road trajectory. I just said the road network can be treated as a graph G, so it has a series of vertices and edges. The vertices of the road network are the intersections of two or more roads, and the edges of the road network are made up of each actual road. Then we use P to represent a series of agents. Vehicles moving on the path in the network it can be seen as a series of road trajectories. So it is necessary to convert road trajectories to the original path P. Then we'll get map-matched trajectory. Map-matched segmented trajectory T is a set of connected road segments, which projected from T to G. It can be represented as a set of connected graph vertices in G. A more important reason to use map match is that because of the GPS error or poor accuracy, some vertices are not in the road. They might be located inside the building or places next to the road, as we can see in the picture. So map match method can handle north location points. We use HMM's VATB algorithm to find the most likely matching candidate sequence. Therefore, by using map matching method, we map trajectories to the road network. All trajectories are converted to sequences of vertices and agents. Now let's focus on the modeling part. We will extract features from road network by road network embedding, and our task is to learn low-dimensional potential representations of vertices in the road network. Since the road network is a spatial graph, being inspired by word-to-vector, we use node-to-vector as an effective method. This method can be mainly divided into two steps. The first step is to acquire the network vertex sequence through the random walk. And the second step is to learn the vertices embedding vectors through the concept of word-to-vector. For network G, the method learns to convert the vertex to the function f. So the vertices of the road network can be converted to a multi-dimensional vector. For each vector u, NSU is defined as its neighboring vertices. Then we just need to optimize this objective function. Based on eigenspatial assumption, when vertices are treated as both source vertices and near neighborhood vertices, the embedding vector is shared, so we can express the conditional probability formula in this form. There are two main relationships within network, which are homomorphy and structure equivalence. Homomorphy is the closely connected neighborhoods in network, such as vertices U, S1, S2, S3, and S4. Their relationships are homomorphy, where the so-called structure equivalence refers to vertices that have similar function in the graph. These vertices may not be adjacent to each other and may even be far from each other, such as U and S5 in the graph. We can wonder that the feature vectors of vertices which have same relationship should be close or similar. So we want to obtain closer trajectories through training. We need to focus on homomorphy. In our model, we choose DFS as sequence sampling methods. DFS is a search that goes farther and farther away from the source vertex. The feature vector excludes reflects the homomorphy relationship in the network. Therefore, we use DFS to take random walks, obtain sampling vertices, and extract features from the network. If trajectories are relatively close, then their converted vectors are also close in the vector space. As the model is applied to the field of trajectory similarity query, so we add a distance weight conditional probability in the objective function. So the formula based on spatial distance can be converted into this form. In order to query similar trajectories more quickly, we also use Atrey method. Atrey divides the hyperplane by dividing the principal. Similar data vertices should be closer to the binary tree, and a split hyperplane should not divide similar data vertices on different branches of the binary tree. Then traversing the binary tree and the path from root vertex down is sorted according to the query. Since it is too expensive to calculate the probability of the entire graph vertex, the method of negative sampling is used for training, and the model is optimized by SGD. Finally, each vertex is converted to a feature vector by network embedding. Trajectories are converted to sequences of vertices mapped to the road network. Now let's look at the dataset we use. The taxi trajectory data comes from Patil in Portugal and T-Drive in Beijing. The road network data is obtained from OpenStreetMap. You can see the number of vertices and edges in the table. Then we named our method as RNE and compare it against some baselines. Firstly, we evaluated the efficient of the methods with top K query, which is querying the most top K similar trajectories. K is 5, 10, 20, 35, and 50. When Atrey was not used, the performance of Rn decreased with the increase of K. As we can see in the picture, when the K is greater than 20, Rn is not as good as torch. But when Atrey query algorithm is used, Rn each time outperforms other methods on both protocol and T-driver datasets, which shows that the query time can be greatly reduced if your index is built by Atrey algorithm. Then we defined the self-similarity measure as an average rank value for all such trajectories to evaluate the accuracy of this model. We took 1/10 of the data in 2 datasets at random and collected them. Then we changed the dropping rate from 0.1 to 0.6 to distort the trajectories from downsampling. We can see that if the sampling rate is too low, then the trajectory is a linear motion of 2 vertices, and the continuous sampling is not correct. So our method filters out the noise points through the zone network and extract the feature information of the zone network. Thus, experiments show that our method is robust in assessing trajectories compared to other methods, and low sampling rate and noisy environment. So in conclusion, there are 3 main contributions of our method. We're the first to perform embedding learning in trajectory similarity assessment that consider both the topology and the spatiality of road network. Secondly, we built a road network embedding model, extract features from road network, optimize the spatial correlation of loss function, assess trajectory similarity where converting trajectories to vectors. On real data set, our proposed method improves at least 62.2% faster than the compared method, and being robust to trajectories with low sampling rates and noises. The novelty of our function is that we change the similarity measure of the trajectory to that of the feature vector and make the time complexity of the trajectory similarity computing to a linear correlation of converted trajectory length. Okay, this is all I want to talk today. If there are any questions about our work, please ask.
Okay, thank you. Thank you for your presentation. Actually, you are not the author, but can you take the question?
I'll try it.
Okay. Yeah. Okay, great. Okay. Yeah. Is there any question from our evaluation committee members or the attendees? Also, okay.
Hi, this is Naimul Khan. I have one quick question. The efficiency that you have listed in the table, does this efficiency include the time required to create the embedding model features, like extract the embedding model features?
Yeah. When the relative distance between two trajectories becomes smaller, the trajectories become more similar. So based on this theory, we design our method, and the target of our paper is to obtain closer trajectories and aging vectors through training.
Okay, understood. So that's why the embedding is more efficient. Okay, thank you.
Yeah.
Any other question?
So what is the motive?
Can you explain more details about how you optimize the spatial correlation of loss function? Can you hear me?
Yeah. I can't hear you clearly.
Okay. Let me ask again. So how you extract the features from road network and how to optimize the spatial correlation of loss function in your network?
Okay, in word to vector, words are converted to vectors via skipgram. Here, vertices in graph are converted to vectors through our network embedding method. So we use node-to-vector as an effective method. We have made improvements to this method that we add a distance weight conditional probability in the objective function to handle spatial characteristics of road network. Yeah.
Okay.
We're the first to perform embedding learning in trajectory similarity assessment. Also, we use a noise method in order to query similar trajectories more quickly.
Okay, yeah. Thank you.
Okay. Next question.
My question to you is, you have chosen one particular form of this conditional probability. What is the motivation of using this conditional probability? Why not some other form?
Do you mean the map matched function?
You just go back to your earlier slide. Yes, this one. Now come to next slide.
Sure.
Yes, this one. So when you are defining this distance weight conditional probability, what is the motivation of using this particular form of conditional probability? Why not some another form?
Where its trajectories are relatively close, their converted vectors are also close in the vector space. So we need to consider their spatial parameter. As the model is applied to the field of trajectory similarity query, so we need to add a distance weight conditional probability in the objective function. The W is the distance weight conditional probability. And we can use such as European distance in it to handle this problem. Yeah.
Okay. Thanks.
Okay. I actually we still have less than 1 minute. Is there any short question possible?
Yeah, maybe I have a quick question.
Okay, great. Roger, thank you.
This is Roger. Thank you for the presentation. Just a quick question. You said that in your model you use map matching as one of the steps. Map matching also has errors. So I mean, it depends on the sampling rate, but it's not always 100% accurate. So did you investigate, there are different map matching techniques. Some are more accurate, some work better with low sampling rates. So did you investigate the influence?
Yeah, map match method is good at handling noisy location points. Where our model can't be used in check-in data. For check-in data is generated in the building or some location, not on the zone network. So I think this method is more suitable for trajectories on the road. The algorithm works by calculating multiple matching candidates within a certain area around each input GPS location. Yeah, that's all. Yeah.
Okay.
Okay. Thank you, Roger. Thank you for the presentation. Yeah. Okay. Yeah. Let's go to the third paper.
Okay. Thank you.
Yeah. Thank you. You can close your desktop. The third paper will be presented by Alexander. Okay. Are you ready?
Yes. Yes.
Prepare. Please share your presentation. Share your slide.
Sorry, the share button's. Oh, now it's good. Okay.
Yeah.
I'll do that now. Okay.
If you're ready, you can start. Okay.
Okay.
Yeah. Please.
So hello. My name is Alex Berman. I'm a PhD candidate in computer science at Texas A&M University. And shameless self-promotion, I'm defending this coming Tuesday, and I'm looking for jobs. So if anyone likes this work, feel free to email me or go to the my website. That contact info will be at the final slide as well. I'll be presenting ThingiPano, a large-scale data set of 3D printing metadata, images, and panorama data renderings for exploring design reuse. Okay. So 3D printing is going to change a lot about how we make things, how we purchase things. For example, this application where you can scan your ear and it'll send you a 3D printed earphone that matches your ear shape and which determine colors. But not only that, but 3D printing can be a cost-saving measure to many companies and many industries, where instead of shipping lots of subcomponents from one place to another, they can 3D print more in a more central location and save money that way, but from designers all over the world. And companies like Adidas have been doing this. So the 3D printing process can be sort of generalized to 3 steps. One is you have to obtain a design fabrication, usually a 3D file, convert that 3D file to machine code specific to a particular type of printer, and then upload that machine code to that printer and operate the software and hardware needed to create the object. For over a decade now, the website platform Thingiverse has been a place for people to upload, download, modify, and print many different 3D printable designs. But it's not easy to download and print something because 3D printing is not what you see is what you get. There's a lot of things that go into 3D printing, so one design that works on one printer might not work on another, might not work for all materials. And if you intend it for a certain domain, let's say outside versus indoors, there could be different things that you'd have to take into consideration that are not obvious. For example, on this comb the very thin walls to the right disappear actually when printed in a lot of common printing software, because the thinner than the resolution of a printer, so the software says, oh, I can't print that, and just skips it. But it's not obvious by looking at 3D file that this would be the case. And there's several issues that can go wrong while printing, and that only appear in certain types of designs. So there's a big open question of someone who's trying to 3D print is what can be printed. And to help with that, we're releasing this ThingiPano dataset to help facilitate reuse of 3D printing designs. This includes over 1 million different design metadata with associated images and user metadata, as well as multi-view 2D representations that can be used in many more traditional neural network and machine learning techniques. And we'll discuss that later. So first, I'll talk about the scraping methodology used for downloading all this data, talk about the different types of metadata, talk about how this metadata can give us more insight into 3D printing as a practice, then talk about the images and 3D file representations in ThingiPano, and how they can be used in self-supervised machine learning examples, and talk about all the different types of feature work that can utilize ThingiPano. So all these designs were downloaded between 2018 and 2019. And then after we downloaded all designs, we went through and collected all the usernames and downloaded the metadata for the associated users. First, we'll talk about design metadata, which we'll break into 3 different categories: designer annotations, community annotations, and site information. Designer annotations include the title of the design as uploaded, a description about what it is, how to print it, a license saying, do you have to attribute it, can you use it for commercial use, a category, which is one of, where the designer picks from one of 80-ish different things in Thingiverse, different categories, such as this example, which is a dice tower, where someone can toss a dice at the top, and it'll go down the spiral staircase and roll to the bottom. And they assigned this category toys and games dice. Another very interesting thing here is remix info. So this gives ideas of provenance of what type of 3D file came from. So in this case, it was remixed from an existing design. So someone either was inspired or took that 3D file and made it into this design. And it was also then remixed into 6 other new designs. So people then took the 3D files from this and then made new designs from there. Another interesting thing is the Thingiverse customizer, which allows for parameterized designing right in the web of 3D files when the designer uploads code instead of just a static 3D file. In this example here, in the customizer, you can enter an IEEE Big MM and ThingiPano as 2 strings, and it'll generate this name tag that viewed from one angle it shows one, and viewed from another it shows the other. And subsets of this type of metadata have been used in different types of publications. In this one, looking at various types of reuse and how they can be used across different domains, different categories for unintended purposes. As well as looking at when this customizer app was introduced, that the number of designers that joined Thingiverse rapidly increased. Next, we'll talk about community annotations, which includes who likes which design, who makes which design, which is when a user uploads an image and a description of saying, here's proof that I made this particular design, as well as comments, collections, which are when people basically make a curation of different designs they'd want to print, watches when they want to be updated when certain things are printed, as well as tags. Tags could be used by any, can be added by any user on Thingiverse, not just the designer. And so for customized designs, you can see a lot of things related to customized, but for original designs that want remixed, you can see there's a lot of holders, toys, 3D scans. And again, subsets of comments on Thingiverse have been used in various papers, including this one that looks at high level what type of knowledge people seek on Thingiverse. Lastly, site information, which includes statistics for each file that was uploaded as part of a design, as well as banners that are in the bottom left of the images shown at the bottom, which show whether the design was featured, is featured for education, was it removed for various reasons of violating Thingiverse policy, and various other reasons. Also is collected as user metadata for over 200,000 users, which includes statistics of the design metadata we mentioned before, as well as who they followed and are following. Groups, which are like forums they could subscribe to in Thingiverse. A bio, which describes who they are, maybe their profession, maybe where they are. 3D self-attributed 3D design skill level, as well as tools such as printers and printing software, design software. So next, talk about a metadata example use case. In particular, we're going to look at what the Thingiverse users see and reuse in Thingiverse. So we can break up users into basically two different groups. Surprisingly enough, is that users tend to publish, if they publish any designs at all, they'll publish almost entirely original design works that are not remixes, or they publish almost entirely either remixes or the results of a customized application. Looking further, we can see that the vast majority of users start off being a non-designer, and that most of them actually stay that way. So the majority of people on Thingiverse are really just downloading and printing objects, not necessarily uploading new novel designs. And that it's evenly split among those two other categories. But any type of application that wants to facilitate reuse of 3D printed designs has to treat these three different types of users a bit differently. Next, we're going to talk about design files. So these are very important to understanding and facilitating reuse, as the description metadata in design is very short and doesn't fully describe the functionality of a design. So for example, on this top right, the summary says it is a phone holder for the car to be used as a navigator, but it doesn't really say where it fits on the car. But if you look at the image, you can see that it says where to attach different versions of this to the car, and actually has additional images for saying attached to the steering wheel or to the DVD tray. And there are over 1,800,000 different images across all the designs. In addition to these images, we've rendered these 2D depth map cylindrical projections of the 3D files. This was adapted from ThingiPano code, which at one point in time was the state-of-the-art for 3D file classification and retrieval. However, we extended it to do multi-views of the X, Y, and Z axis and at a larger resolution. However, it is worth noting not all designs have 3D files. Some are tutorials and for other things like laser cutting, and that not all 3D files are well suited necessarily for printing. Some are uploaded and are never really printed ever. So that's worth noting. So we can think of a 3D object as a distance away from the object. So let's say we have something like a Connect scanner or something similar. We can view the 3D object as this depth map as we rotate around it. So given any object in Thingiverse, we created 3 cylindrical projections of what this depth map would look like for any given file. So given over the million different designs Thingiverse for all the 3D files, we have these depth map images as shown on the right. And these can represent lots of different types of geometries, from functional items to models to toys, to simple geometries to complex artistic designs. And one thing to note is we did not normalize orientation, as many designers may upload files with the intent of something being printed in a certain orientation, as the orientation would matter. As on the right, you print flat to the build plate a lot of the times to increase strength and the ease of printing. But in some cases, you need the extra resolution, like when you're printing out a lithoplane picture as on the left, in which you need the XY resolution so it's printed vertically. And also it's worth noting that multiple objects were not split. And because some things are printed while being interlocking. So we built a machine learning model on images adapted from Gomez et al.'s work in self-supervised learning, where we train text embeddings from the design metadata, from the descriptions, and use those vectors to then label images from the same designs. So that way we're training a network to say, given an image, what type of designs are associated with it. And given within that network, you can see when you attach you input this picture from Amazon that shows a phone microscope adapter. They get similar designs from Thingiverse, as well as a iPhone tripod mount that serves a similar purpose. We also applied a similar network for 3D file classification, where you input each of the 3 panoramas into one neural network, which then, after the max pooling layer, it gives us a visual representation of each panorama, which then we can concatenate and make it predict these textual embeddings, which we use WebGeoVec, TF-IDF weighted vectors. It will give us a sense of what semantically similar 3D files exist for a given object. So this is represented by this given input. Given this battery cover, we can get a battery cover for a drone, for a toy model, as well as a different battery cover entirely. So next we'll talk about what ThingiPano can provide for future applications. So it can be used to research many different communities and domains as subsets of the metadata have in the past, such as assistive technologies, as well as understand differences between designers and other users, such as customizer users and non-designers. It can help bootstrap many multimedia and multimodal models from the ground up, because it is over 1 million different images. It can also help train closed domain 3D printing natural language processing models, investigate how to identify function of 3D files from visual features, as well as transfer learn to smaller, to different problems where you might have a smaller subset of data. In addition, it can help with multimodal search. So, for example, on the right here, we can see an actual real-world 3D scan, which then returned a different design from Thingiverse. It can also be used to build knowledge graphs to explain 3D printing terms and practices in various different applications, as well as help with copyright and terms of service violation detection systems. And metadata such as likes or even tags can be employed to train collaborative filtering or other both content-based and hybrid recommender systems. And finally, it can help with design assistance, where in a CAD application, it can provide printing terms related to what you're designing, as well as maybe designs that are similar, and help people in the design process create something that's printable, but also informed by what's been made previously. Finally, as a teaser of, so as an addendum, I've made this website called How DIY, or Howdy for short, which helps search for 3D files in Thingiverse, not only by overall best search results, but as well as by category. So you can see with books, you can see bookshelf models, models of books, as well as functional things that help with reading. And so it is a more simple thing than Thingiverse, where you can navigate the different features, as well as see prices of different ways of printing it, which is not a feature on Thingiverse, as well as provide recommender systems to help guide people and recommend different things based on what they view and different things they see on Thingiverse. In addition, I built a closed domain question answer system from ThingiPano data to help answer different questions users might have about 3D printing. Sorry, I'm running a little bit over. Thank you so much. Does anyone have any questions?
Okay, thank you, Alex. But sorry for that. You only have less than 3 minutes to take 1 or 2 questions. Okay.
Sorry. Thank you.
Yeah. Is there any question from the committee members or the audience?
Hi, Alex. Thank you for the presentation. Very interesting work. So I just have one quick question. So originally in the beginning, you said that one of the challenges with 3D printing is it's not always what you see is what you get. And you gave a nice example of the comb, right? So my question is, how does ThingiPano help in solving such problems?
That's a great question. So one of the best ways of solving basically what to print is knowing lots of examples of what has been printed. And so there's two sides to that. One is being able to see several examples relating to a given query or a given design could help with that, as well as knowing popularity metrics, such as if something's been made a bunch of times, you know it's generally printable. As well as things like comments can also give tips of saying, because if there's a common issue that's given with a given 3D file. Here, let me find this slide. Users will make mention of it, and there's a lot of discussion around that.
Okay, so essentially, like crowdsourced data is gonna help solving that. So yeah, that's actually a good way to like solve that type of issues. Because as you said, if it has already been printed, I'm guessing there will be discussion among the users about like what things to modify, what things to change to make a better printing out of it, right? Okay, good.
Right. So ThingiPano can help because if you do some type of content-based analysis, you could determine what type of questions are common with that, or if you can identify common issues from the textual data.
Perfect.
You could help guide people in that way to determine what is printable.
Okay, very good. Thank you.
Yeah. Okay, we can only have 30 seconds. Any other question? I think it should be fine. We can take one more question.
Maybe a quick question. Do you have any metrics on how many people have started using the data? I mean, the data is already available, right?
The data is available. I don't have much data, and I don't know of many examples besides me of people who have used it. There's been a few people that have started and so forth in GitHub, but I don't know beyond that. If anyone has used it. One thing I would like to mention is if anyone has any other questions, feel free to email me. I'll be happy to answer anything.
Okay. Thank you for the very interesting presentation. Okay, time is running up. Okay, so
thank you.
Yeah, let's go to the final paper at this section. Pradeep, please prepare your presentation.
Sure. I'm trying to see how do I share my screen. Okay, here you go.
Yeah. Okay, great. If you're ready, you can start your presentation.
Sure. Hi, hello everyone. This is Pradeep Atrey presenting live from Albany, New York, and it's after midnight here, around 1:35 a.m.
Oh.
All right. So today, I will be presenting my work on GeoSecure-R, which is secure computation of geographical distance using region-anonymized GPS data. And this work was done with Vikram Patil. So let me start this, presentation by posing a few questions to ourselves. Do we use smartphones? And I think the answer to this would be most people use smartphones. Now, the second question is that often we see that there are many apps which try to access our location, and many times we have to allow our location to be accessed by those apps in order to get location-based services. For example, Fitbit, in this case, is trying to access the location from the phone. The third question is very important. Are we concerned that we are being tracked by third-party apps? And there are private information which can be actually revealed by location information. For example, what are the places you visit, and your political affiliation, your religious affiliation, and other things can be known by this private information, by location information. And there are a number of apps these days actually which are trying to access our location, and they are using it for different purposes. All right, so then we started thinking about this problem like this guy, but we didn't smoke. It's not good for health. We tried to address this question: how do we provide LBS while ensuring users' location privacy? So let's look at the use case scenario here and the system and threat model. We have a user which is considered honest, and users would like to use location-based services, but they would not like to share their location. On the other hand, there are cloud service providers which actually are used for storing our data, and they are honest but curious. So they would like to provide services of storing the data, but also they would like to see our data. On the other hand, there are LBS providers who are also honest and curious. So they would like to provide location-based services, and at the same time, they would like to use our data. So, the communication between these entities is considered to be secure. And then, of course, there are external adversaries who are always kind of malicious, and they try to attack either LBS providers or CSP or users. So under this threat model, our goal and contributions of this paper is the following. So we are trying to develop a method which will allow users to use certain distance-based location-based services while preserving their location privacy. So that means we can preserve privacy, location privacy of the user, but we can actually calculate how much distance they traveled, and based on that, whatever location-based services can be provided, we are looking into those. And at the same time, we are trying to reduce computational overhead and transmission cost of data between users' device and the LBS providers, and also maintain data confidentiality from curious CSP and LBS providers. If you look at past works, there are a number of works which actually have focused on number of aspects, like they have focused on privacy. Some of the works have focused on security by doing encryption and all. And there are, also issue of compression, because we need to actually reduce the size of the data in order to have bandwidth efficiency and all. And also then what utility is there with the data. So if we compare our work with the existing works, so we see here that we are actually able to obtain the goal of privacy, security, and compression. Plus, we also are able to provide location-based services which are based on the location. So what's new here is we are providing a single approach which will allow distance-based LBS with location privacy, data confidentiality, and compression. We started thinking about this in this direction, and so one of the naive approach actually could be that from user's device, we just keep the first point of the trajectory and then send the differential points to the LBS provider or to the CSP. So in this case, CSP need to compute distance, and for distance, typically Haversian formula is used actually, which contains a term which is cosine terms, a product of cosine terms. So what actually we did here, because in this term we need actual location latitude information of 2 points if you want to compute the distance between 2 points. So we estimated kind of this to 1, and then if we kind of approximate this to 1, we get a lot of error. So around 15% errors were there, but at the same time we don't need to provide CSP the actual location. We just provide the differential data. Then the next step could be actually, because there's a lot of error here, 15%. So the other approach could be just give the first point, and then we send the distance between first point and the second point, that is dlat and dlog, so differential latitude and differential longitude, and or actually the distance between those two points. And we send it to CSP or LBS provider. So what it will do here, it will calculate the value of that beta parameter, and it will actually, based on these three parameters, it will optimize, it will find out what is the optimal value of beta, and that beta value will be used for rest of the differential data, and then to compute the distance in rest of the data. And therefore, here in this Everson formula, we can use beta, optimized value of beta here. So this actually method resulted into lesser error, around 5%. But we were not happy with that. We came up with another method here. And this method is based on the region anonymized information. So here, again, we are keeping the first point at the device as a key, and then we are sending the region information to the CSP and LBS provider. And the key idea here is the following. So in a region, if we have two trajectories, and the difference between any 2 points here will be same as the difference between any other 2 point on another trajectory. So if we can have a displacement mask between this trajectory to this trajectory, we actually are doing that. So we are choosing a point in the region PK, and then that point along with the differential data, we are using this point to calculate the corresponding point in the rest of the trajectory, and so on, and compute the distance. So we presented a proposition in the paper that if we choose any 2 points on one trajectory and another 2 points on another trajectory, and if their differential latitude and longitude is same, and then the distance actually will be same between the 2 points. The key steps here in this method are, so one part is here, and these steps are to calculate the key, which is the first point, and then the differential data, and then this differential data is sent to the CSP or LBS provider, and then we correspondingly compute the other points based on a chosen point in the region, and then offsetting that point with the other points. So we experimented this method on a data set of Microsoft GeoLife dataset, which is widely used for trajectory computations and analysis. It contains approximately 18,000 GPS trajectories. It was collected by 182 users over 3 years in Beijing, China. We also did some pre-processing of the data in terms of removing stop points and removing some erroneous points from the series, and also ignore trajectories with less than 5 points. So we present our results here, and we see here that the percentage error means that the distance which is calculated using actual trajectory, that means without any location privacy, and the distance which is calculated by preserving privacy, the differential, the percentage error between these two is denoted by epsilon pi here, and that we compute, and also then we average this error for the entire trajectory for number of points, and we report here for these 3 methods, and we see here that the percentage error is actually lower in GeoSecure-R compared to these other 2 methods. Here you see that number of trajectories, the most of the trajectories, they lie here actually in the error range of 30, 20% and so on. And here in GeoSecure-R, actually they lie here in close to 0. Most of the trajectories are between 0 and 10. So we deduce here that the mean of the average percentage error is actually quite low in case of GeoSecure-R compared to other 2 methods. Similarly, we also analyzed trajectory utility function, and to utility basically we define by the distance calculated using our method and the distance calculated using actual data without location privacy. And we see here that utility in GeoSecure-R again is very high compared to other two methods. And we can see here that for GeoSecure-R, that the utility is computed between 0 to 1, and it's in the range of 0.9 to 1.0 compared to other two methods, which are around 0.7 or 0.8, something like that. We also did privacy and overhead analysis for our method, and we presented a proposition and provided its proof that privacy loss in our method is negligible. It's equal to 1 over 10 to the power 12, which is a very, very small value. Compared to other two methods, GeoSecure and GeoSecure-O, we see here that compared to GeoSecure-O, the privacy is here in region anonymized, and here is on Earth, whereas compared to GeoSecure-O, it is anywhere on the longitude. At the same time, we also compared our method in terms of computational overhead and storage overhead with a peer method here, and we see here that compared to this method, our method is computationally less expensive in terms of we just do only 4 multiplications of these magnitude and 2 subtractions, compared to this method actually does exponential function and so on. In our case, we don't have an encryption and decryption, but at the same time, we are able to achieve confidentiality of data because we have only the differential data. Without key, we can't get the actual data. And also, the number of terms which are stored in our case is also quite low. Right, so conclusion is happy ending here. This method is able to calculate users' travel distance, and it is able to protect users' actual location. So, and it reduces percentage error with respect to other two methods. And the potential applications of this method would be, it can be used in fitness trackers or urban planning queries or auto insurance companies, which are actually looking for, let's say, how many miles you traveled in a day, or what are your driving habits, how many times you stop and how many times you actually do speeding and all. So from distance, we can always calculate velocity and acceleration kind of thing. So what next? In future, we would like to explore this method for other secure services, for example, secure search of nearby places and secure traffic congestion monitoring, etc. Okay, thank you. That ends my presentation.
Wow, thank you for your presentation, Pradeep. Okay, and we have sufficient time for Q&A. So yeah, the committee member and the audience, please raise your hand to have some question. Or just unmute your mic, it's okay. Is there any question? Okay, one question from me.
Sure.
Could we go back to the experiment result? You saw the region, I mean the approach comparing. Yeah, I know. The next.
Oh, okay. All right, this one.
Next one.
Oh, this one.
Yes, the overhead analysis. I'm curious about that. Your approach based on the region. Okay, right. So if we enlarge the region near to like the whole Earth, how about the overhead, the privacy and the overhead in this case? Actually, the region would be very limited, the size of the region, right? The coverage. If we try to enlarge the region, in that case.
So, so region actually, we mean that it could be several 100 kilometers region. Within that region, it would actually, this method will work. So, yeah. So the distance between 2 points of 2 different trajectories within a region of 100, several hundred meters would actually be same, let's say in a city and so on. So privacy leakage here is that we would be able to find out that in which region the user is. However, we like a state, we cannot find out where exactly in the state or in a city that user is. So that's a kind of a anonymization we are doing.
Okay, this one, some some kind of the limitation, I mean the constraint on the region, right? Yeah. Okay.
Yeah.
Okay, good, understand. Is there any other question from the audience?
I have a question.
Yeah, please.
Thanks for the presentation. It was very easy to follow, and I know the concepts are pretty complicated there, but the simplicity of the method is the most appealing part. Maybe you made it too simple. The question, which I have is that why even constrain it to the region?
Right. So we want to have location privacy. So we don't actually want to reveal where exactly the user is, and so there are a number of methods to do that. However, those methods, they have their limitations in terms of accuracy and the distance which they can calculate. However, if we choose this method, we have a limitation of, okay, so that the user will be there in this region, but that region is so large that still we can consider that it is the user's location is anonymized. But this method is actually able to give us the same, almost the same distance, very, very small error compared to the actual distance of the user. So did I answer the question?
I'm sure I didn't ask my question clearly. My question really is that why should we even limit it to the same region? I mean, why? Right. I mean, that constraint itself can also be relaxed, right? I mean, you can use pick a point.
Yeah, I think I got your question. So the reason for that is that within a region, the latitude and longitude values, they don't change drastically within certain hundreds of kilometers and so on. So if the differential data is same, then it's going to help.
Got it. Thank you.
Thank
you.
Yeah. Any other question? Is there any other question from the committee member? Oh, Roger, please.
Yeah, Pradeep, thank you much for the presentation. Just a quick question. I'm not sure if this makes any sense here, but I mean, so your method is to compute direct distances between point A and point B, right?
Yes.
I mean,
so basically, over user's trajectory, distance between 2 points of the trajectory.
Yeah. So is there any? I mean, there are a number of LBS services where you have sort of multiple points, right? It's not a straight line. Could this method be adapted for that, or once you have multiple points, you kind of reveal more information?
No, it can be adapted to that. Yeah, because we are looking at the differential data between 2 points. So as long as we have 2 points, we can get the differential data. So even if there are multiple points, or if it is not in the same line, the method is going to work for sure.
Okay.
Okay. Yeah. The time is just reaching the 20 minutes. So thank you for your presentation, and let's thank all presenter again. Thank you everyone for joining this best paper selection session. I think our evaluation committee members will catch the big contribution from the oral presenters for the 4 candidate papers. And I suppose to make a conclusion by collecting oral evaluation results from our committee members. And then the program co-chair will announce the winner of the best paper and the best student paper at tomorrow's that's the town hall section, right, Rajab? Okay. Yeah. Yeah. Please come back again. Look at the
Yeah, you are right.
program.
Sorry to
Yeah.
interrupt. Yeah.
Okay. Yeah. Please
Tomorrow's
try
Tom session.
Okay. Yeah. Please try to look at the program and come back again to make sure confirm who will be the winner of the best paper and the best student paper. Thank you, everyone, again. Thank you.
Okay. Thank you.
Yeah, thank you.
Thank you. Bye bye.
Bye bye.